Hello YouTube. Today I'll be going over problem 324 from Griffiths C&M, and this says to solve Laplace's equation in cylindrical coordinates. And Laplace's equation is a Laplacian of v is equal to 0, or del squared v is equal to 0. And in cylindrical coordinates, del squared v is equal to 1 over s partial by partial s partial v over partial s plus 1 over s squared partial squared v over partial phi squared plus partial squared v over partial z squared is equal to 0. And for this problem, we're assuming cylindrical symmetry, and we also want to accommodate for when it's a line charge, which goes towards the natural log of s. So in cylindrical symmetry, del squared v over del z is equal to 0. So this reduces to 1 over s partial by partial s is equal to 1 over s partial by partial s times s partial v over partial s plus 1 over s squared partial squared v over partial phi squared is equal to 0. So in order to solve this, we have to use our separation of variables. We want to guess the solution when it's the product of two functions. So v of s of phi is equal to s of s and phi of phi. I have written the s's and the phi's in different colors so that we can kind of distinguish between them. It is a little hard to tell, but I will do my best to differentiate between the two. So when we plug this into our differential equation, we have 1 over s d by ds, because now when we have these in here, it becomes a ordinary differential equation. So 1 over s d by ds times s d by ds of s and phi of phi plus 1 over s squared d squared over d phi squared phi of phi s of s is equal to 0. Our first step is going to be multiply everything by s squared and divide by s of s and phi of phi. So we get s over s of s d by ds times s d by ds s of s plus 1 over phi of phi d squared phi of phi over d phi squared is equal to 0. So in order for these to add up to 0, they have to be equal and opposite constants. So let's say this one is C1 and this one is C2, for instance. Also, we want to take in mind that this first term is only dependent on s, and the second term is only dependent on phi. So I've written that here, valid. So in order for them to be valid, they have to be each equal to an opposite constant, meaning they both add up to 0. So C1 plus C2 is equal to 0. So let's say s over s d by ds s ds over ds is equal to C1, and 1 over phi d squared phi over d phi squared is equal to C2. So if C2 is less than 0, we would get exponentials. And in order to show that, I'll do that real quick. D squared phi over d phi squared is equal to phi C2 if it's greater than 0. We want C2 less than 0. So if it's greater than 0, we get this. The second derivative of phi is equal to phi C2. We can subtract that and have it set to 0. So the second derivative of phi minus phi C2 phi is equal to 0. So we run our auxiliary equation, our characteristic equation for differential equations. We say phi is equal to e to the lambda phi. So phi double prime is equal to lambda e to the lambda phi. So then we get lambda squared minus e to the lambda phi minus C2 e to the lambda phi. And this exponential is not going to 0 for any finite number. So we have lambda squared minus C2 e to the lambda phi is equal to 0. So that means that our 0 occurs when this is equal to 0. So lambda squared is equal to plus C2. So our lambda is equal to plus or minus C2, the square root. So we get phi is equal to e to the plus or minus the square root of C2 phi. And we can't have that because our angular term must be a periodic function and it must repeat itself. Its value must be periodic. So that means that phi of phi plus 2 pi is equal to phi of phi. And in order for us to ensure that C2 is negative, we're going to set C2 is equal to minus k squared, because any number, when you square it, is positive, and when we multiply by -1, it's negative. So this means it's going to be negative. So now we get 1 over phi times the second derivative of phi is equal to C2 is equal to negative k squared. So now our second derivative is equal to negative phi k squared. And we can just add that to the same side. So our second derivative of phi plus k squared phi is equal to 0. And we use the auxiliary equation once more, where phi is equal to e to the lambda phi. So if phi is equal to e to the lambda phi, phi prime is equal to lambda e to the lambda phi, and phi double prime is equal to lambda squared e to the lambda phi. But this time we have a positive right here instead of a negative. So now when we have this, we plug this in, we have lambda squared e to the lambda phi plus k squared e to the lambda phi is equal to 0. So we factor out the e to the lambda phi and we get lambda squared plus k squared. This is where our zeros are going to occur. So lambda squared is equal to negative k squared, or lambda is equal to plus or minus ik. And when we plug this back into our equation, phi is equal to C1 e to the ik phi plus C2 e to the minus k phi. And that's not good enough. We want to now rewrite this using Euler's identity. And Euler's identity says e to the ix is equal to cosine x plus I sine x. So phi is equal to, after doing some algebraic gymnastics, we get phi is equal to C1 cosine k phi plus C2 sine of k phi. And the book has C1 as A and C2 as B, so I'll be rewriting phi as A cosine k phi plus B sine of k phi. And since phi is periodic, so phi of phi plus 2 pi is equal to phi of phi. And that means it's periodic, so k must be an integer. And it also includes 0. When k is equal to 0 here, we just get a, which is a constant, and that's perfectly acceptable. So that this is our solution, but when k is equal to 0, we just get phi is equal to a, and that's part of our solution for later on. So if C2 is negative k squared and C1 plus C2 add up to 0, then C1 is equal to positive k squared. So now we have s over s, d by ds, s ds over ds is equal to k squared. So we can multiply by the capital S, or the orange S, or I think it might look red on this page, and this one might look purple. But anyway, we multiply by it and we get s d over ds, s times ds over ds is equal to s k squared. And what I did is I expanded this out, so I still have this s over here. And right here we're going to do a product rule, so ds over ds, this is the derivative of s, times the derivative of capital S plus little s times the derivative of capital S again is equal to sk squared. Now this just reduces to 1 because we're taking the derivative of just s, and that's just 1. So, but this becomes the second derivative, so we have s times the first derivative of s plus s times the second derivative of s, and that's equal to sk squared. So I just rewrote this again, equal to sk squared. Or I'm sorry, I multiplied the s right here. So s times the first derivative plus s squared times the second derivative is equal to sk squared. And just subtracting the sk squared, and now I have it set equal to 0. And this is known as a Cauchy-Euler differential equation. So s squared d squared s over ds squared plus s ds over ds minus sk squared is equal to 0. It's a Cauchy-Euler differential equation, and solution to these are of the form of s is equal to s to the n. So that means s to the prime, s prime, or the first derivative, is equal to n times s to the n minus 1. And s double prime is equal to n times n minus 1 times s to the n minus 2. And n minus 1 is equal to n squared minus n. Okay, so when I substitute these into the differential equation up here, s squared times n squared minus n times s to the n minus 2 plus s times n times s to the n minus 1 minus s to the n k squared is equal to 0. So s squared times s to the n minus 2, that's just s to the n. S times s to the n minus 1 is s to the n. So also n times s to the n minus n times s to the n is 0. So we have n squared s to the n minus k squared s to the n is equal to 0. So again, our exponentials are not going to be 0 for any numbers. So n squared minus k squared is going to be where our zeros lie. So n squared is equal to k squared, or n is equal to positive or negative k. So this gives us the solution that s of s is equal to c s to the k plus d times s to the minus k. Unless s is equal to 0, which we have to consider as in our angular function. So when k is equal to 0, our differential equation becomes s squared d squared s over ds squared plus s ds over ds, and that's equal to 0. And in order to solve this, we can say, okay, well, let's set the first derivative equal to v. So now we have s squared v prime plus v s v is equal to 0. And this is a first order linear differential equation. And now we can say s times v, we can factor out an s. S times v plus sv prime is equal to 0. And we can divide by an s. So v plus sv prime is equal to 0. So sv prime is equal to minus v. And now we could say, well, okay, well, v prime is equal to minus v over s, or dv over ds is equal to minus v over s. So dv over v is equal to minus ds over s. But so minus dv over ds is equal to minus v over s. Sorry, I think I rewrote it again. dv over v is equal to minus ds over s. And when we integrate that, we get natural log of v is equal to the natural log of s plus c1. And then we exponentiate it, so we get v is equal to e to the c1 over s. So then we kind of undo the substitution again. So we say, okay, well, v is equal to ds over ds, which is the first derivative of s. So ds over ds is equal to a, I'm renaming it as a constant, over s. So this is just a separation of variables. So ds, and then we integrate, is equal to a over s times ds, and s is equal to a natural log of s plus c. Okay, so now we want to take the angular component when k is equal to 0, so a cosine k phi plus b sine k phi. If k is equal to 0, we get a cosine of 0 plus b sine of 0 plus is equal to a. If we solve the differential equation, d squared phi over d phi squared is equal to 0. So phi, normally normally when we have this type of differential equation, we say, okay, well, phi is equal to b phi plus a. But this is an unacceptable answer. And the reason is because it doesn't return to its initial value. So if we did this, we would go, okay, well, phi prime is equal to b and phi double prime is equal to 0. What's the problem? Well, it doesn't go back to its initial value. That's the problem. So our solution then would be v of s of phi is equal to a naught plus b naught natural log of s plus the infinite sum. Now, because we said that these were a product of two functions, and these two functions were a cosine k phi plus b sine k phi, and c s to the k plus d s to the minus k, we can rewrite it as this right here, because these constants here are gonna include all the other constants, because everything in front of it was just constants. So we just want to have every term in front of every term have a constant, and we multiply them together because it's a product of two functions. So, and we included the k is equal to 0 case right here. This is our a term, which is when our periodic function has a 0, and this is when our exponentials are 0. We get b naught natural log of s. So, and this does include the potential for a line charge, which is b naught natural log of s, and that's included in our solution. So our total solution is v of s of phi is equal to a naught plus b naught natural log of s plus the infinite sum from k is equal to 1 to infinity of s to the k times a sub k cosine k phi plus b sub k sine k phi plus s raised to the negative k c sub k cosine k phi plus d sub k sine k phi. Anyway, that's all. Thanks for watching. I hope you learned something from this video.